Welcome to the Deep Dive, the place where we turn massive stacks of technical papers into pure, distilled knowledge. Today, we are undertaking a deep dive into the tiny component that basically redefined the entire world.
Yeah, the one that enables everything digital you interact with, the transistor.
Exactly.
It's often called the greatest invention of the 20th century, and that's not hyperbole at all.
Not at all. We're talking about the core of the whole electronics revolution.
It's the key component in every modern device, from a, simple sensor circuit to the massive CPUs in our
I
computers.
have billions of them now. It's incredible.
Billions of these tiny little switches.
So our mission today is pretty straightforward. We want to give you a really deep understanding of the two foundational building blocks of all solid-state electronics.
We're going to dig into the diode and then the transistor.
Right, we'll explore what they're made of, how they actually operate, and why that three-terminal device, the transistor, was such a huge breakthrough for digital logic.
I think we have to start with the definition, though. So a transistor is a three-terminal semiconductor device. Its job is to regulate the flow of current, or voltage. It acts as an electrically controlled switch, or as an amplifier for signals.
But you can't really get to the transistor without first understanding its predecessor, right, the two-terminal diode.
You really can't.
So let's start there at the foundation. The p-n junction. This is where chemistry meets circuits through a process called doping.
That's right. So we take a semiconductor, which is usually silicon, and we intentionally introduce impurities into it.
We mess with it on purpose.
Exactly. So if we use a material like boron, which has fewer electrons to share, we create what's called p-type material.
P for positive.
P for positive, yeah. This material ends up with an excess of empty spaces where electrons should be. We call them holes.
And those holes act like they're positive charge carriers.
Correct. And then on the flip side, if you dope the silicon with something like phosphorus,
That one has extra electrons.
it has extra electrons, yeah. It's a donor material. That creates n-type material, which gives us an excess of free electrons. Those are our negative charge carriers.
Okay, so the magic, the real basis of all modern electronics, happens when you join a p-type and an n-type piece together.
When you form that p-n junction,
So what happens right at that border?
well, there's an immediate localized reaction. The free electrons from the n side see all those empty holes on the p side, and they just rush over to fill them.
But it doesn't just keep going forever.
No, it stops almost immediately. And this creates a very thin area right around the junction that's now empty of any mobile charge carriers. We call that the depletion region.
And that region is the key, isn't it? It creates this natural electrical pressure.
It does. It creates a potential barrier. And that barrier is everything. It's what makes the p-n junction a nonlinear device. It's not like a simple wire where the current just flows. Here you have to push hard enough to get over that barrier before anything happens.
And that barrier has a specific voltage.
It does. For silicon, it's typically around 0.7 volts. For an older material like germanium, it's a little lower, maybe 0.3 volts.
Okay, so because of this built-in barrier, the diode basically acts like a one-way street for electricity.
One-way valve, yeah.
So if we forward bias it, we connect the p side to positive and the n side to negative.
Yeah.
We're pushing against that internal barrier.
Right, and once your voltage gets past that 0.7 volt threshold, whoosh, the current flows very easily. An ideal diode at that point is like a perfect conductor, zero resistance.
But if we flip the battery around, reverse bias it.
Then you're just making that internal barrier stronger. You're widening the depletion region, and the diode acts like a perfect insulator. It blocks all current flow.
So that unidirectional flow is its whole purpose.
That's its defining function.
That makes sense for controlling flow, but
Yeah.
why do we care so much about this in the real world?
Well, think about the power coming out of your wall socket.
It's AC, alternating current.
It's AC. It's oscillating constantly. But almost every single electronic circuit, your phone charger, your computer, it needs steady, direct current DC to work.
Okay, so the diode is the bridge.
Exactly. The diode's primary job in power systems is rectification. The process of converting that wavy AC signal into a usable, if still a bit bumpy, DC signal.
And the simplest way to do that is half-wave rectification.
Right. You use just one diode, and it literally just chops off the negative half of the AC wave. You're left with only the positive pulses.
But the downside seems pretty big.
Oh, it's substantial. It's dramatic. The maximum theoretical efficiency for full wave is 81.2%.
That's more than double.
It is. It cuts energy waste, and it gives you a much smoother supply of power, which is critical for all the sensitive electronics we use today.
Okay, so the diode solves the power conversion problem. It's the one-way valve.
Yeah.
But it couldn't solve the bigger problem of control, taking a tiny signal and using it to manage a huge flow,
For that, we needed an upgrade. We needed the transistor.
which is really just two diodes stuck together, in a way.
Fundamentally, yes. It's formed by connecting two PN junctions back to back, which gives us our three terminals, and it provides the two functions that really launch the digital age: switching and amplification.
Switching is the big one for computers. So
It's the killer app. It means a tiny input signal can turn a massive flow of current completely on or completely off millions or billions of times a second.
that's how you get the zeros and ones of binary.
That's binary logic. And amplification is just as vital for the analog world. Think about a faint radio signal. The transistor grabs that tiny signal and boosts its strength so you can actually hear it clearly.
Now, when we talk transistors, there are two main families we should mention.
Yes. There's the BJT, the bipolar junction transistor. That one is a current control device. A small current controls a large current.
Okay. And the other?
The other is the FET, or field effect transistor. This one is voltage controlled, and we have to mention it because modern chips are almost all FETs, specifically MOSFETs.
And why is that?
Because they use almost no input current to switch, which makes them incredibly power efficient. It's why we can cram billions of them onto a single CPU.
Let's focus on the BJT for a second, though. That idea of current gain. I think the truck analogy really helps explain it.
It's a great one. So imagine a big truck's air brake system. You have this huge tank of compressed air ready to stop the truck. But the driver doesn't release all that air directly. They just press a pedal, which releases a tiny puff of air. That tiny puff, that's our small base current.
And that little puff of air controls a bigger valve.
Exactly. It opens a relay valve, that's the transistor, which then causes a massive rush of air from the tank, the large collector current, to slam on the brakes. A tiny input controls a massive output.
That makes perfect sense. So let's look at the anatomy. The BJT had three terminals: emitter, base, and collector. How are they physically different?
They are very different, and it's absolutely critical. The emitter is moderately sized, but it's heavily doped. Its whole job is to be the source, to supply a ton of charge carriers.
Okay, it's the gun.
It's the gun. The base is the control gate. It has to be extremely thin and very lightly doped,
Why so thin and light?
so that the carriers from the emitter shoot right through it without getting stuck. You want them to pass through to the collector as easily as possible.
Which brings us to the collector.
The collector's job is to collect all those carriers. It's the largest of the three terminals, and it's only moderately doped.
And why is it so big?
For a very practical reason: heat. It has to dissipate a lot more power than the other two parts, so it needs more surface area.
Okay, here's a question I've always had. An NPN transistor has two N-type regions, the emitter and the collector. Why can't you just swap them in a circuit if one burns out?
That is a fantastic question, and the answer gets to the heart of the invention. They are absolutely not interchangeable, because the emitter is so heavily doped to be a great supplier, and the collector is moderately doped and large to be a great collector.
They're built for different jobs.
Completely different jobs. The device is asymmetrical by design. If you swap them, the current gain, that amplification factor, just plummets. It barely works.
So to make this asymmetrical device actually work as an amplifier, you have to bias the junctions inside it in a very specific way.
Precisely. For what we call active mode, you always forward bias the emitter-based junction. You turn it on so it has very low resistance.
That's the input.
That's the input valve. And at the same time, you reverse bias the collector-based junction. You turn it off, creating a high resistance field.
And that specific setup is what lets the tiny base current control the big collector current.
That's the secret sauce.
Okay, let's connect this back to the digital world. You said transistors are how we represent binary data.
Yes. And it's interesting because you can actually build very basic logic gates with just diodes and resistors. You can build an AND gate, for example.
Where both inputs have to be on for the output to be on.
Correct. But there was a huge piece missing from that simple diode logic, something it fundamentally could not do.
And that was the on.
The ability to invert a signal. You can't build a NOT gate, an inverter.
And a NOT gate just flips the signal, right? A HEH input gives a low output.
And vice versa. And without the ability to invert, you can't build feedback loops, you can't build memory cells, you can't build a real computer.
So the inability of diode logic to create an inverter is why the transistor became absolutely essential for computing.
It's the technical reason it was the killer app. The transistor in switching mode is a perfect inverter. A high GH signal to the base turns it on, pulling the output, low W. A low signal turns it off, letting the output go high GH. Modern computing is impossible without that.
And beyond logic, we see them everywhere in like high-power control systems.
It's the perfect bridge. Your microcontroller runs at, say, 3.3 volts. That can't possibly drive a 12-volt motor.
No way.
But that little 3.3-volt signal can easily turn on a transistor, which then acts as a heavy-duty switch for the 12-volt path to the motor.
Well,
Low power controlling high power.
you can also do clever things like current steering, right? Like in a traffic light.
For sure. You can have a single output from a microcontroller that just flips from, say, positive 5 volts to negative 5 volts. And depending on that polarity, a set of diodes and transistors will automatically steer the current to light up either the red lamp or the green lamp. No need for big, clunky mechanical relays.
It's just an elegance of control, really.
It is, controlling massive energy flows with almost no effort.
This has been a fascinating journey, and if you're listening, you now really hold the key to understanding almost all modern electronics. We went from the simple one-way valve, the diode, using one PN junction for rectification, and getting up to 81.2% efficiency.
To the three-terminal controlled switch, the transistor, which was made possible by that careful asymmetrical design of two PN junctions.
And remember why the emitter and collector are not interchangeable. It all comes down to their physical construction and doping levels.
And that critical distinction between a current-controlled BJT and a voltage-controlled FET is so important for understanding why modern chips are the way they are.
That's right. The FET is the powerhouse of modern, power-efficient computing.
And we'll leave you with this final provocative thought. All of this knowledge, everything we've talked about, it all hinges on the physical limits of that PN junction, that 0.7-volt barrier in silicon. The initial challenge for engineers was just about overcoming that barrier. But now, the constant, fierce push for lower power consumption in our devices means designers are desperately trying to find new materials with even smaller barrier potentials, or even entirely new designs to sidestep that physical constraint completely. The work on that tiny junction is, perpetually, never really done.